Namaste. I, JVN Narendra Kumar Chal, Assistant Professor in Department of Science and Technology and Faculty of Education and Methodology in Jyoti Vidyapith, Women's University, Jaipur. So in today's session, we are going to discuss about grid computing. So when we talk about the grid, so just the first thing come in the mind is something like uh, built from some small parts. So coming to the next slide. So what is the grid? So the term grid comes from an analogy to electric grid. That means uh, it is pervasive access to power. Similarly, grid will provide pervasive, consistent, and inexpensive access to advanced computational resources. So grid computing is all about achieving greater performance and throughput by pooling resources on a local, national, and international level. So when we talk about the grid, it is some kind of distributed computing. So when we talk about the distributed and parallel computing, so the distributed computing also subset of parallel computing. So when we distribute a task into multiple subtasks and then we compute it, so we simply say it is distributed computing. But when the resources are located remotely over the globe, those can be anywhere on the earth or anywhere in the universe. So we are just using the resources and then we are computing or we are doing some advanced computing using this. So we say this is the grid computing. Now we talk about the scalable computing. So we can just differentiate by the performance and interplanet grid. Just like you have a computer here, then we have some rack server, and then we have distributed computing. We have the network in a building, and then we talk about the network or the earth, and then interplanet. So what is interplanet? It is from one planet to another. So the network is still growing, just like from a single system to a network, and then it is connected to a server, a big network, and then a building or some kind of institution or a local place, and then it is to Earth. So when we talk about the interplanet grid is moving forward, then the performance is increasing. Just like we are using more resources to compute the things, just like we have one person to do the work, so the efficiency will always will be low. But when the same task is assigned to 10 people, so it is obvious the work will be done 10 times faster. So everything is fine, but what is the barriers here? So when we deploy 10 people here, so we have to pay more. We have to manage those people that they can work properly or not. So here some administrative barriers are there. First one is individual, second one is group, and then departmental, then campus, then might be state, national, and globe. So these are the barriers in scalable computing. Just like how I can scale them. So when we talk about the grid computing, so it's about large scale resource sharing. It's spanning administrative boundaries like central processors, storage, network bandwidth, databases, applications, sensors, and so on. The problem solving in dynamic or multi-institutional environment. Now we talk about some resources that are located remotely, like how we can use the resources those are remotely, or how can I avail my system for the grid computing if someone is doing some computation. So organizing graphically distributed computing resources in grid computing. So why this is required? Just because uh, they can flexibly and dynamically allocate the resources we have, just like they can use the all resources and uh, complete the task. Now, providing such capabilities where sharing is highly controlled, clear definitions of exactly what is shared, who is allowed to share, and the conditions under which sharing occurs. Here in grid computing, there are some limitations also. There must be the security in the data. So how they ensure that? Just like I give an example, like I have my PC here, and I want the grid computing. Let my computer use for some kind of computation. So there are some websites out there. We simply can sign up and we can say, ki, okay, you can use my laptop through the internet. But we have to keep our system on at that time. So when they use, what they do, they just test, they just run simple tests in it, and then they find out that this is feasible to them, and then they use the resources, just like your memory and your RAM, and might be your browser also, and the processor. So these are the things, and these are just controlled by them remotely. So when we are not doing anything, then we can avail it for the grid computing. Now we'll talk about the elements of grid computing. So we can say this is resource sharing, coordinated problem solving, and it's for dynamic multi-institutional virtual organizations. Now, when we talk about the resource sharing, so it's computers, data, storage, sensors, networks, etc. And then sharing always conditional. Just like if I want to avail my system for them, so it is always something like that I want to share or not. So if I am sharing that, it's fine. I'm trusting those people. And what are the policies? I have to read that. What is the negotiation level? What is the payment? So most of the times it might be free of cost. We are just contributing to the community. Now, second one is the coordinated problem solving. So it's like beyond the client server model, the distributed data analysis, computations, collaborations. It's like there is no client server. Client server model here. So what is the thing? When I have assigned a task, at the same time, someone else is also assigned the task. So who is computing fast and who is doing something better with a better efficiency, and that it takes a minimum time. So whom we will consider, just like uh, the less time and the better results. It is obvious. So the distributed analysis is done there, computations, and the collaboration of the systems will be considered. Now we talk about the dynamic multi-institutional virtual organizations. So this is the community overlays on classic organization structures. They might be large or small or static or dynamic. There might be a small organization with 10 people, or it might be some big institution where thousands of people are using it, or it might be scalable also. That means we can just scale that. Now we talk about the virtual organizations. So virtual organizations, just I have talked about. So you will see some more details here. So it's a set of individual or institutions defined by a set of sharing rules. It's like how much resources we can share or for how much time. The sharing is highly controlled with the resource providers and consumers defining clearly and carefully just what is shared. What we are sharing, it is completely auditable, and the logs are everywhere in the system. So it is highly controlled. And what are the rules to set up all these things? This is always clear. For an example, the set of application service providers, this storage service providers, cycle provider, and consultants engaged by a car manufacturer to plan a new factory. They are restricted to do something just like if they are working there, so okay, it's fine. You just work here. Another example we can take for the industrial consortium building a new aircraft. Now we will talk about some more formal definitions of grid. Now a grid is a system that uh, coordinates resources sharing in the decentralized manner and different virtual operating systems. Just like I have multiple operating systems, those are providing the resources to do some tasks. So here we are just saying that what is the grid? Grid is something which is coordinates resource sharing in a decentralized manner. As previously discussed, it is some kind of many system task, and which is not centralized. Just because we are assigning tasks to some people, and then we are just taking them. Second, grid system that uses stand, open, and general purpose protocol interfaces. So it is clear that there will be a standard, and it will be open to all, and some protocols will be followed there, and what interface the user can avail or make it avail to the grid resources. Now, delivers non-trivial qualities of service. That means non-trivial qualities. When we talk about some fault or something like some error, so it might be there, but at the same time, a task is assigned to multiple systems. That means a number of systems are doing that same task, and the result will be produced on the basis just like which is the best and which is coming fast to the master node. So there is a system which controls. So there might be a decentralized, but there always be a system that manages all. So the metadata can be stored on a node. But when another system becomes the master node, it also saves the metadata. Now, in this, it guaranteed bandwidth for application, and it guaranteed CPU cycles and latency. So these are the things which ensure in the grid computing. Now, we talk about the applications of grid computing. The computational grid applications are biomedical research, industrial research, engineering research, and studies in physics and chemistry. So these are the things. First, we can see the poster, the science today's things for just like we are having some experiment here, some groups. So we just can just make the system available. How many people are using that? Just like here, a physicist is using some supersymmetry working group on the supersymmetry working group, and then the phenomena group. So there are multiple groups. There are desktops, computers, multiple schemas, storage available there, and the softwares. So here we are talking about the first. Next, when we talk about the e-science, so it is a large scale science carried out through distributed collaborations, often leveraging access to large scale data and computing. So when we talk about the e-science, so it's an important paradigm of science and engineering research that grids are an important approach. So there are still many unsolved research issues, and there are no consensus as to the best level infrastructure. However, this is to be expected. This stage of the grid project, it's already some clear success in emerging, and this will motivate exciting research and some more progress in the e-science. Next, we see the TerraGrid. So TerraGrid is a e-science grid computing infrastructure. So it's an important project developed by the National Science Foundation (NSF). So it is the simple grid network. So when we talk about the TerraGrid, so it's an e-science. So it's an e-science grid computing infrastructure combining resources at the 11 partner sites. The project started in 2001 and it was operated between 2004 to 2011. The TerraGrid integrated high performance computers, the data resources and tools, and the experimental facilities. So resource included more than pref loops of computing capability and more than 30 petabytes. So it's a large amount of data of online and archive data storage. So the 30 petabytes is very much. With a rapid access and retrieval over high performance computer network connections. It's like these all are connected through some high performance computing devices. It's like some supercomputers are there, and the network connectivity is also some kind of very fast. It's like here written, this is 10 gigabytes, multiple 10 gigabytes of this connection, and these all connections are at this speed. So researchers also access the more than 100 discipline specific databases. So there was a databases managed there and everywhere. So the TerraGrid was coordinated through the grid infrastructure group. It's GIG. You can say that's GIG. So at the University of Chicago, working in partnership with resources provider site in the US. So in the University of Chicago, there was a GIG which was just looking at the TerraGrid. Now next we see the infrastructure of this. So this is the extensible backbone network. So there is a hub out there, and this is in LA, Los Angeles, and this is in Chicago. So these are the hubs. These are connected with 40 GB per second speed, and now this hub is also connected to another one. So here the speed is 30 gigabytes per second. So these are multiple nodes which are connected here at some multiple purposes. Now, when we see the UK science grid, so this was connected to these areas. This was in Oxford and Cambridge and London and Southampton and what places. Now, we talk about the applications. So it's a national virtual observatory. So aeronautical surveys produce terabytes of data, just like some aeronautical data and the meteorological department data and the surveys. These things collect petabytes or terabytes of data. So it needs to be stored somewhere else, and if some analysis can be there, so this is only done by the multiple PCs or multiple resources. So a single system can do that. Even the supercomputer also. So the data set will cover sky in the different wavelengths like X-rays, optical, infrared, and radio. The challenge to make this accessible to a general research community, heterogeneous data producers and consumers. So the data is produced in various modes, like it's heterogeneous or homogeneous data. Heterogeneous means that that's a different data at different nodes or different places. Resource in the grid are data sets in the compute. So these are the applications. So from the next section, we will talk about the high energy physics. So this is all about the introduction to grid computing and the applications of this. Thank you.